Yeah, so just repeating again, we have the templates of the code and the links on the chat here. Let me know if you can access them. I see right now, so I see 4 pluses that we have some access to the templates. But let me know that those of you joining now, that you can also have access to the templates. Let me know, okay?
Hi, sorry, where is
yeah.
the template?
On the chat, in the chat right now, but maybe you didn't.
But I see only classes there.
Okay, okay, so yeah, I will post it again. So thanks for letting me know. So if at any point you don't access some of the resources or something, then let me know. So we'll start with a quick classification example, and then we'll move to the actual example of all of this stuff regarding the deep metric learning. And the deep metric learning, the fun thing will be that there is so much to do that I think we can make quite a few tutorials of that. And also my PhD thesis very related to that. Okay, so let's try then to move on. So we are right now 1 minute over. Maybe somebody else will join a little bit later. Så... Jā, paldies tev. Prieks, ka pievienojies. Tā, so I will post again the templates for the first ones. So the Jamboard, now let me share back to the Jamboard. So I also don't want to waste our time. As I said before, we'll try to be very precise, as precise as I can. So anyways, so the idea will be that we will look at deep metric learning, and the simplest one of those is the contrastive loss. That was by the LeCun, who invented quite a few important things in deep learning, naming the convolutional models and the all sorts of energy models, and a lot of work with RNNs, if I remember correctly. So, and he was the one of the first who also invented contrastive loss, and I think initially it was for the signature verification, really like the research even before this last resurrection of the AIs and deep learning. That was like before the last winter, I think. So, and here, if somebody knows more about that, you can share. But so here the idea is that we have samples of different classes or the same class. We have model of this, like the weights are the same for any sample as it would be in any classification task, but actually the image is not that great. So I need to actually improve it a little bit. It's really strange that I did not notice it immediately, is that there's actually 2 times called the same models. That would be the same way as it is for any classification task. The only difference is that it will produce not the classification probabilities, but the embeddings, and these embeddings would then be placed in the latent space, and we would operate with them. We will try to cluster together those embeddings that are more similar and like make more apart those embeddings that are dissimilar. And there's actually so much research, and really interesting research, because like how you actually then measure all of those similarities, how you manage the loss. There are many things about it, but we'll start with very simple model and then move to more advanced models. There are some that like recently published that are really powerful. With the less hyperparameters, we always need some hyperparameters for these models. Actually, I just realized that I will need to quickly find some extra images to illustrate some of the points. If some of the points are not clear, then let me know. But like in the very beginning with the first template, we will start with classic classification, and then we'll move to this one. So here, the idea is that we have some samples, and we want to cluster them in this latent space so that from the same class samples are at the same cluster. The interesting thing is that like for the for these kind of deep metric models, it's common that samples that are mislabeled or really similar to the real samples, or there is actually maybe hard to see, but there are like the deers and then there's like horses. So this is like CFAR 10, I think, or something like that. And then some of those samples look really similar, and they are in the same group as the others. And this is like a kind of intentional feature of deep metric learning, because you could use it also in a zero shot learning setting. So this is what you have in let's say the Apple Face ID and all sorts of voice ID technologies and biometric identifications, is that you would not retrain the model every time when you have the new class in your data set. You would train it once and then add many classes later, and they would cluster together by the similarities, not by the training the model priors itself. So here there's some example of what I mean by that is if you train it just by the softmax here with the cross entropy, with the probability distributions, if you map it in the PCA on 2 dimensions, there is no guarantee that it would cluster well, and it's also no guarantee that there will be any structural semantic similarities between those samples. For example, like let's say there will be one, like if this is a MNIST, right? There is colors, right? So the orange one is 1, right? Then there is a green one is 2, and whatever. Like all of the samples are just clustered together without any visual similarities. So here again there's more interesting situation where the 1 is clustered together with 7 that is very similar to classes and like visually, and they just like optimize the space that they are at the same location. And then there's another approach where again these two are together here. And if you would introduce some samples that were never seen, you would get the situation that they would also cluster in the same location using just the encoders and the embeddings of the kind of the semantic similarities. So here there is again one example from my experiments that I did some time ago already, is what I trained the model on eMNIST, extended NIST, and then I selected out a specific number of classes that I never showed during the training, just for the inference. And if I show them for the inference, I see that they cluster really well. So, but there's another caveat here. This is a PCA. So the principal component analysis, dimension reduction, if you would use anything like TSNA or UMAP or something, there's a high probability that the image would look not as believable, because they would optimize the distances, not the kind of hyperplane of the projection. So the hyperplane of the projection would be more reliable, because we want to, even if this image would look better on TSNA, it would be more reliable to analyze it if you just project it on one plane. Because we don't want to fool ourselves of seeing that some of these cluster really well, and then in reality they are not clustering that well, because later in inference you need some kind of reliable method for estimating, let's say, the radiuses or standard deviations or something for. And the idea here for the zero-shot learning is that, for example, if there would be a lot of faces here, and then you have some new faces coming in here that was never seen in the training, you would want to have the enrollment samples, right? And then some test samples that you compare them. And all of this is done without training. That's why that would be a zero-shot learning. So if you have any questions while I'm talking about this, you can type in the chat or maybe try to ask the question, and we'll soon get to the point. So, and then, yeah, I think the good way would be if I just now explain some of the basics, and then we go back to that classification sample implement stuff, and then come back to this. So like it would help us, I think, to better grasp the concept. So I think like the idea itself, all of this is not really that difficult, but you see also in the code. So there's a lot of ways how people like formally describe these contrastive loss functions and other functions. I will show you how I like to write them down, and also explain some of the notations, because as I found out that some of those notations are not consistent across the papers. So here there is one way how to describe the contrastive loss, and the idea is that for each batch you would have different kinds of samples. So you would have similar samples and dissimilar samples. So the similarity could be estimated by many things, not only the classes, but classes is like a classic way how to do this quickly. So for the similar classes, you would have here as a 0, and then for dissimilar would be y1. And then you have this dv. So the dv is actually distance matrix, or the distance between any of two vectors of the embeddings that are coming out of the model, and the m is the margin. So here I think I need to have extra image that I forgot in the very beginning, but I will quickly get it. So margin. The idea is that you want to do two things. So, and also I forgot to mention about this thing. So here this is a bit confusing notation, but lately used very often. Like if you look at the papers some, let's say 5 years ago or so, this was not so often used, but now this idea is that this is basically you can write it as a max as well. So this is a max of 0, m minus dv. Maybe let's ask in the chat some first question if you're engaged enough. So what actually is this function? Like we use it all the time. Maybe you can identify it. So let's type in chat, what is this name of this function? Actually, I know at least two names of this function. One older type of name that used like 10 years ago, I guess, in the papers, and some that you all know. Yeah, Yevgeny is saying that this is Relu, that is one name. That is correct. So yeah, the Relu or the hinge function basically. So I think the like really old models with SVMs and stuff, they use the hinge functions, and that is basically the idea. But let me quickly show you some images. I'm trying to desperately find some that would be nice. Hopefully this one. Kind of forgot to get them properly. So here. Yeah, I mean, yeah, the notation. So Christopher is writing that the notation is weird, but this is what they use in the FaceNet, and I think in some other papers as well. So this is just the max. Here, that's good to know at least like, so can I show you them? So here the idea is following that. You have some, like the anchor sample is actually the anchor and P, those are the two pairs that are the similar pairs, and then the anchor and M are dissimilar pairs, and then we have also there is the margin, and the margin is actually in this sample the red part. The orange part, there is an extra margin, but let's forget about that one. So the idea is that here, for example, in this area, you see that the M, that is like a sample from another class, dissimilar sample, and also here this N, they are very close within the margin of the red area, that is the margin area, to the A. So we would calculate this with the Euclidean distances. There could be also different other distances, like cosine distances. They are in somehow much better. Sometimes there's also different like ways how you can normalize your embedding space and have even more interesting distances, like Mohabonese distances, and there's quite a few options. And here the idea is that now, after the proper training, you would push out these samples of the margin area and like magnet in these P samples that are the positive ones to this area. So the way how it's written right now here, this is maybe not totally the optimal way, because they could collapse to just one point in the embedding space, and that also is not very beneficial, because if you think here about this sample, you have like new faces of people that you want to cluster. It will not cool if some samples are collapsed here, and then like some sample, when the person is a little bit turned ahead, it's somehow jumps a huge distance to some other collapsed point here, and stuff like that. So, but at the same time, this is a good start for us. So far good, hopefully. Just this basic idea to explaining. Then let me show you how I like to write this down. So here, copy this one. The I think more clearer way how to write it down would be something like this, where you have just the positive pairs and then the negative pairs, and then if you want to like specifically show what is the positive pair and what is negative pair, there are some ways how people usually write these notations. I can show you some of them as well. So copy, and then drop in here. So one notation would be something like this, for the positive pair, where you have the embedding, and then let's use some kind of Euclidean distance of this embedding. Also, for keep in mind that if you want to use Euclidean distance, you need to somehow constrain the Z embeddings. Otherwise, like if they are unconstrained, they would just go to infinity, and then to be really bad. So one way is to use the L2 norm. Okay, so that's it for like brief intro. If you have seen all of the stuff for first time, probably quite overwhelming stuff. So what is DP? Okay, Christopher is writing. So this is a Euclidean distance between, in this case, not in all cases, Euclidean distance between the same class samples here. The dn would be Euclidean distance between not same class samples, and the z is the embeddings. So you'll see that in the code, probably easier to kind of understand the basic concepts regarding this during the seeing the code. So we'll do that. Okay, so let's move this one here, right? Okay, so and then let me share the code. So you should have the template ready for the classification. I will try to show you a little bit how to do the proper model loading very quickly, and then also, so I prepared basically the template that you can run on the Google Colab, for example, or you can run it also. Okay, so I see actually one interesting thing. So help me out in the chat. Is the screen flipped for you? Okay, so the resolution is quite poor. What could I do? Maybe I have some ideas. Okay, so let me think. I could try to share the screen. So this is gonna be a little bit weird, but let's see. Okay. So let me know, is it better now? So where is the chat window? Okay, I see a chat window. Much better. Okay, cool. Good to know. Good to know. Okay. Interesting. Interesting. Okay, hopefully it will be good enough for this time. So I have some ideas how to improve this for the next time. Okay, anyways, so I will try to zoom in and try to get us working on this. So there are two parts missing in this stuff. One is the loss function. Another is the model. So with regards to model, I would like to use the pre-trained model from the Torch Vision. So this one is the MNIST, like the fashion MNIST. So with the clothes, like really dumb, simple dataset. But we will like I don't know, like in next tutorials or so, use a little bit more advanced datasets. Just for this one, let's use this one. So bear with me a little bit. I need to quickly find my stuff around. So just don't want to waste your time, and look at my notes as well a little bit. So here we will use the encoder. Can you share the file again? Right, definitely. So please, if you don't have the access to the files or so, let me know. So here there will be the Jamboard and the file. And we will have another file as well today, hopefully. Let's see how far we get. So here we'll use the Torch Vision. Torch Vision. Oh, why didn't show up? Torch Vision. And it's interesting that this stuff is messing around me. So there's models. In the models, we have a huge library of really good models. So, but just to illustrate this task, we don't need that powerful model. So the pre-trained okay, so yeah, sure, definitely. Christopher is saying that it would be nice if I shared the template files like earlier, like day before. I definitely do that for the next time. So yeah, so like I did not kind of thought about that, but of course there will not be that much code now. It will be more about the logic itself. So the encoder, pre-trained ResNet. So this is pre-trained on the ImageNet. That means that you'll have the output of, there will be actually two things. One is that the output is the 1,000 classes, right? But now we have actually 10 classes, and the other thing is the input is RGB image. But the images that we have now, they are grayscale fashion items. So they're like trousers, shorts, and stuff like that. That is the dataset. Maybe let me show you around a little bit. So one thing that I will also going to do to help out those of you who cannot get along so fast, I will drop in some screenshots in the Jamboard so that later on you can catch up. But let me show around. So here I made in the top of part some debugging maximum length of dataset. So my computer is a quite old MacBook, so I cannot like run the GPUs properly. So I usually run them on the clusters, or you can use that in the Google Colab. And the batch size, the learning rate, the headless. So the idea of headless is that I don't want to display plots immediately on my like screen. I want to save them as images. Then check if this is a CUDA, then I assume that this is not my machine where I work with the debugging, and then I want to run the whole training. And here I also have some part of the creating the folders for storing the results. So in this case, results are just very simple images for the accuracies, the train test losses, and stuff like that. Then we download the dataset. Then we prepare the dataset a little bit. So one interesting thing here that you need to take notice is that if I prepare the torch dataset and give the index of the class here, I have to add it inside the extra dimension. So normally this would be just a scalar value, scalar long integer of class, right? But to make this properly, I need to, so the batching procedure wants to have the vectors, so I just add additional dimension here, so at the end it is so it is 1 comma like that, I think, the shape, and then when it will be batched, it will be batch comma 1 like that, so it should be squeezed. But otherwise, if somebody knows better way how to pass those indexes in the PyTorch, you can let me know. So then there is a training and testing datasets. One is shuffled, another one is not shuffled, so we can have always some reference images. Then there is model that we will do now. Then there is a optimizer where we select those parameters that we want to train. There are some metrics. We can add more metrics if we want. Then there are 2 loops. So one loop is for the training and test datasets. So it's always better, in my opinion, to have same kind of structure for the code for both of them, so you don't have 2 separate code bases. Also here, if this is a test dataset, there would be actually a cool thing if we just use the model eval. So we can set it to evaluation mode. Evaluation mode is important if you use the dropouts. So there are maybe some other cases where that is important, but primarily to turn off the dropouts. So if you don't want to do the Monte Carlo dropouts and stuff like that with the Bayesian model, so you should leave them off like that. So this is then the train. So, but if it's not added here, don't worry, not that big a difference. One difference that also can be right now important is set grad enabled. So for the training, we want gradients to be enabled. For the testing, we don't want them to be enabled. So just to make a little bit faster, lower footprint on the GPUs. Okay, so I will actually add these lines to the Jamboard, so you can catch them up later. Let me see. Everything is really slow because I'm now copying so many screens. Okay. So let's see, can I get there quick? So then will be the slide number 6. Dropping in the code there. So in the slide number 6 we have now those lines if you want to catch up later. Now if you go back here, then there is the training, testing loop, whatever. So what did this one, the gradient enabled, the idea is that basically you can even control some parts of the model where you want gradient and where you don't want gradient. That is very often used functions. But here the idea is that you want to minimize the procedures in GPU when you don't need them. So if you think about how the backprop works in the PyTorch, the idea is that, for example, if we have the loss backprop here and inside the loss, so imagine this would be inside the backprop, then it would do the some weight, right? Weight, find the weight, and then it would calculate the gradients, and then it would also accumulate those gradients. So if we call backprop multiple times, the backward, it will just plus the gradients together, and it will always keep for every weight the gradient matrix. And so if you set gradient enabled false, it would not do this procedure at all. Like it will just skip all of the gradient calculations and adding them to the weight gradient matrix. So that is a little bit of help for the speed up and reducing the memory footprint. And now at the end there is a few metrics and plots, so we just draw the stuff. So that's it. So it's really simple code, but hopefully efficient enough. If somebody have ideas how to make it even smaller without losing the way how it's written to show the features, then you can let me know it later. So here, let me show you how to use properly pre-trained classification models, and then we'll move to the contrastive loss stuff. I think it's probable that we could maybe might not make today all of the stuff with regarding the contrastive loss, but we will try to do our best. So here, let's see. We have the encoder, so I will show you how normally you should do it. So you should go inside the model and see what you have there. So if I go inside the ResNet of the Torch Vision, I can see all of the member variables, right? And if I go to forward loop, I even see how it works here. And I see that here there is the flatten, and then there is a FC, this is fully connected layer. Fully connected layer have the input features and num classes. Num class is 1000, and if I just change it here, it will not work because I have pre-trained weights. So what I need to do is fix up that part. So self encoder FC, and we like the PyTorch. I mean the Python itself. It's like great that you can just override anything anywhere. Just like in the middle of like you have some instance of the class, you don't care about the actual class, you just change the member variables, and we can do this here. So linear, and the int features we can copy from what was there before. So we just use this one in features, and with this model I think in let's say 10 epochs we can get 97% accuracy. So like with I think it's quite good. So this one, and the out features is the actual 10 classes. Let us think what we could do, but maybe I can show you also how to access that information in a little bit like not so hard coded manner. So if I use the data loader train, inside that one there is a data set, and inside that one there is a data that is my own variable that you can find up there, and then there is a classes that you can look in that variable, and you will see that they provide the names of the classes. So if you add it like this, or you can just type in 10, doesn't matter. Like if you want to do this quick, you can type in 10 here. That doesn't matter really. So this is one thing. So we solved the output feature. So this is checked, we did it. Yes. So then we need to fix also the RGB inputs. That we can do also quickly. So here there is the encoder con1. We can use the same idea of overriding the stuff. So the way how to do this properly would be to with the ID like the PyCharm that I use right now. So right now I'm using ID PyCharm. So that's really powerful way to do the coding. So there I can just hold the control button or command button and click it like this and go directly to the place where it was initialized, this variable. So if I see that there is a con1, there is a convolution of the 3 input channels, some output channels, kernel size, whatever. So I could just copy all of this and move it there, but yeah, so we could do that actually. torch, and then like that. And if I just check it like this, hopefully it could be okay. So you could even write it down step by step. It's not that difficult. So then here the in features in channels would be 1 because we have grayscale inputs, and the out channels will be the encoder conv previously what there was in out channels. That would be one way how to write down. You could actually write the same stuff for everything here. So that would be great. But now we did something bad, because if we just override the first layer of pre-trained model, that is like hitting out the base on which the person stands, like everything falls apart, because there's almost no point of then the pre-training if we just kill the first convolution. So then to solve this a little bit, to remedy this a little bit, we can try to use either some of the pre-trained weights of the convolutions, or we can maybe use the average of those. So I'm not sure like exactly which way would work better, but we can use one of those. So self encoder con1 weight, and then if we want to copy the actual data, we need to use the data. And then if I want to calculate so let me show you what it is actually. So here the shape is, if I remember correctly, out channels, in channels, and then the weight, width and height, I mean the kernel width and kernel height. So this will be the kernel. And if I want to reduce the in channels from 3 to 1, then I use the mean of dimension 1, and then I need to unsqueeze so that I would match it to the same dimension later. And now, if I want to load those pre-trained weights, I would just do this in this way. So weight, data, and this weight convolution, right? Like that. So the initialization part, I think, is done. So I will copy this stuff also inside the Jamboard, so you can catch up later. Okay, Christopher, I like that Christopher is asking all the time some questions, good questions. So the unsqueeze part, I will show you in a second. The unsqueeze part is just inserting extra dimensions. Let me see, so this is... But wouldn't it be better to use sum? That's a good question. Okay, if you think that the sum would be better than mean over all of the input channels, then not sure about that, but like, because the next convolution is expecting something in some kind of range that is from the mean from previous channel. Convolution is summing over channels. That's right. So I need to think about it. Maybe you're right. I will add the question here. The convolutions are summing. That is correct. But if it's a pre-trained kernel, would it be beneficial? So I need to think about it. You might be right. Sum over mean. So I just wanted to leave the values as close as possible to what they were before using the mean. Just to not throw off the next convolution, but I need to think about it a little bit, so I will do that to do. But here, regarding the unsqueeze, so the new stuff here is actually, so let's say the output channels will be 64, then the input channels will be 1, and then the kernel is here, if you see 7, right? But if we do the mean here, without the unsqueeze, we would get something. So if we do the mean without the unsqueeze, let me see. So after the mean, we get. So let me write down the whole stack. So before we have 3. So this is shape before, like by three channels. Then after the mean, we get this one. Then after the unsqueeze, we get this one. So hopefully that makes sense why there is an unsqueeze on school something 2e, right? Okay, cool. Hopefully that's fine. Okay, the initialization part is ready. Then the forward pass is also quite simple stuff. So out self. By the way, I want to write loss functions ourselves. That's why we're not going to use any like pre-compiled loss functions. That is not the way to go to understand a lot of complicated models. So that's why you're going to use the softmax as well here. Out dim over the. So the first dimension is the batch, right? So this batch comma features or the classes, right? That's why we go over the classes dimension, not the batch dimension. Oh, so that's fine. So this one I also will add to the Jamboard. Okay, where there is the screen snap, snapping the screen, adding this to the Jamboard. Except, okay, it's copying. So yeah, I added that to the Jamboard as well. Okay, so if we go down to the loss function here, what I want to implement is the cross entropy. So where's my LaTeX stuff? So LCCE is then the minus log of y. No, not y, but yeah, y prim of samples that match, basically. Y prim samples that match, or the, let's say, I'm not sure like actually how to write it better. So epsilon, again, maybe like that. Let's see how it looks like. Maybe you know some better notation. If you know a little bit better, let's call it P, because basically the idea later with those contrastive loss, also the positive ones are P. So what I'm trying to show with this one, so the originally it would be just, but if there was like a probability distributions, then you can write it y over logarithm of y prim plus epsilon, like that. If that would be a probability distribution for the y and y prim, but in case of this situation is that we have the indexes. So maybe even if I should write it like IDX, so that would be even clearer. So I want just to select those indexes from the probability distribution that match the ground truth, and then calculate the negative log loss. And then I add a little bit of epsilon to have a little bit of numerical stability. So if I add that one to the Jamboard as well, and let's give you like a small task, maybe. Some would be fun if see if somebody can do this quickly. So here I need to implement the loss function, so that could be implemented like in 1 or 2 lines, basically using that equation that I just showed you, the first one, by selecting the indexes. So I even actually give you the indexes here, and you also have, so you have you need to use a couple of things. You need to use y, you need to use indexes, this vector, for basically if somebody you know TensorFlow, this is the idea of TensorFlow scan. I think it was called like that, to have the selection over the indexes from the arrays, right? So use that one, and you need to use this one. So, and I also will try to write down the shape, so you can try to write the loss function. If you write the loss function here, it's actually you can write it in one line. So then please type like paste it in the chat, so I know that. Let's see who can do this. Hopefully you can. So, and let me meanwhile show you the shape. So shape of this one is the batch comma, like that, right? So these are just the indexes of the classes. So then the shape of this one is just the indexes of samples. Then the shape of this one, so this one is more interesting. So we can read actually we could rewrite, so if you rewrite the task using the second equation, that's fine as well. So it would be b comma classes, so this is a probability distributions. So this is the third shape. So you have three shapes, and you need to write the loss function. Should be quite easy. So just to make it a little bit interesting today, let's see if somebody can do this and post it in the chat. Let's do a quick survey. So if you're trying to do this, then type in plus. If you're giving up, type in minus. If you try to do this, type in plus, minus. So if I know that you're working on it, are you working on it, plus, minus? So if everybody is just giving up and don't know a clue how to do this, then I would not wait. I'm not sure what YIDX is. So one way. So what do you mean by YIDX is? So great to see that some of you are trying to do this. I know Everett's quite smart guy. So, and Yevgeny, of course. Y is in IDX. I'm not sure where you mean by that, but the Y IDX is here, the Y. So this one is the same stuff there. So in this example, Y is the YDX. So if you just make a breakpoint here, right? You could do a breakpoint. So let me actually check. I did not check if this code is actually running. That I should do actually. So maybe I even made some bug here. So if I add the breakpoint, okay, nice to see that most of you are, at least not the most, but many of you are trying to do this. So nice to see it, because it's not really that hard task. okay, it works so far. If you add the breakpoint here, and then just the normal way with the PyCharm, how to do this is just using the Y, then the size and stuff like that, and then you can get all of the stuff here. So yeah, you should try out using the breakpoints to figure it out. I think like not be that difficult. I hope that's not my bad. I forgot one extra thing. So the one extra thing that I forgot is that, of course, you cannot calculate this directly. You need to have the summation, right? As like the backprop then would not kind of make sense. So you need to have some kind of summation or mean. Basically, the mean and summation is the same thing. The only thing is just the amplitude, right? So you could use the either sum or with the larger learning rate or mean with smaller one. Yeah, so I'm not sure did my microphone was on when I was telling this, but you need to use mean or sum basically for having the loss function at the end, of course. So it doesn't matter like sum or mean, just the learning rate amplitude changes. let's do another survey. So should I wait for answer or show it? So plus will be wait, minus will be show it. So in the chat, if you could let me know what you want. So I see one vote for showing the answer. Let's see what others think. Okay, Christopher's wants to complete itself. Everett's as well. So I know Christopher's, Everett's, Aiga as well, quite smart people. Okay, 1, 2, 3 right now. So I think wait, let's say about 3 to 5 minutes more, and then we'll move on to the next part. Yeah, so some of you are asking about this is the same, the phase delta stem. I think it might be the same. So that's great that you remember some stuff that we did before. So the Christopher's answer, this is a funny answer, because if you technically it would work, but it would give not desired outcome. So we still don't have the kind of the proper answer. Wow, that's an interesting answer. So Yevgeny is giving us something really interesting. That is really interesting way to do this. So I'm just thinking about it a little bit. I like it. That's a nice way how to write it down, actually. At the same time, it's not like the optimal way, but it's nice way. So let me think. So Yevgeny was working, the Christopher was working. Let's see, maybe Everett have some answer as well. So I think the Yevgeny's way works. That is good, but it's not optimal. But like if you would write it in the let's say how it's compiled in the PyTorch or other libraries in C or some other language, you would not write it in that way. But the way how you wrote it, I think it's nice. So okay, just not to maybe waste so much more time. So we have at least 2 answers already. So okay, kind of already. I already like the Christopher's way is almost okay, but not really. So okay, and the Yevgeny's way is also good, but it might be better as well. So the fun thing with the deep learning and these function models, you can make all sorts of functions that technically work but do the like not what you want. So here, let's say this will be the mean or sum, doesn't matter. Then the minus torch logarithm, of course, and then you can look up later. I think if I remember correctly, this was the name. So if you look at TensorFlow, and I think maybe even Tiana or some others called this a scan. There's like this strange notation, but you can just write it in like simple terms of the NumPy arrays. So it's a idea that you want to select first the rows, right? And then you select the the columns by rows like this, and you would get like just that one sample by just that one class that you want to include in your loss function. That would be optimal way of doing this. And then plus 1 e minus 8. I think like in many cases they use e minus 8. Actually, funny that Christopher also mentioned that. But the way how Yevgeny wrote, it's also totally fine. You can also write, of course, this equation by expanding the so similar way as Yevgeny to expand y as a probability distribution and then bring it in the front of this equation. That is also fine. So all of these ways are fine. So hopefully that would be also interesting for you. So if you run it, it should train up to, let's say, 97% in few like in 10 epochs or so. Okay. So let me share another template with you. Okay, so I will try to get it quickly. So the other template, copying it, hopefully. So let me know if you can access it. I've just copied in the chat. So this is a contrastive template, simple contrastive template here. Very similar to the first one. Just there will be a few changes. So the model code, we will be able to just copy quite a few things from the first one. And then we'll need to change a few things. And the training part will be a lot different, but we'll get to that step by step. So, okay, my question is first, did you get the second template? Okay, great. We have already a few pluses coming in. Okay, actually, you had a lot of pluses. That's great. So I hope the first sample was fun, because the idea is that it would be nice to start with classification, then you could even plot it in the PCA or whatever, and then compare it with this one, and maybe even combine them, because you can do a lot of interesting things with deep metric learning. Okay, and so I see a lot of pluses. Hopefully others also can catch up. So the idea is here that first you would copy the model code. Basically, we could copy the whole model code, but there will be at least one, but even more significant differences. So if I copy the model code from the previous one, we need to change primarily the forward pass. So let me check. So in the forward pass, we don't need the softmax first, because of course now we are not learning the probability distributions. We are learning deep metric. We are learning some embedding that is in the latent space that describes this feature space. So the one thing that's also maybe a good way to change this is that here we have 10 classes. So now, just to make sure that you understand, is that we can have any classes. So I defined in the top part the embedding size. So if I go back here, there's 32 dimensions. So I can later, maybe in some other time, show you about the embedding size. The embedding size is actually a very interesting property for these models. You don't always need the very large the dimensionality. The larger dimensionality, you actually get this course of dimensionality that you know in many mathematical problems. And also here, if you have like too many dimensions, it will not benefit. Actually, I can see in GitHub a lot of people just throwing at more dimensions, thinking that will help. In general, like you might get a few percent up for your specific datasets, but then in the zero-shot cases, it will hurt you. So here there is a. So what is the embedding? The number of dimensions, right? So the last output before the softmax that we had before, that is called the logits, right? And that is just a vector that we apply the softmax, and then we get the probability distribution. So here we want to learn this last layer. So this will be actually a z. So this will be our embedding, and this output should not be probability distribution. This should be some latent vector. That means like vector that is like a fingerprint. You can think of that like fingerprint of your input features. Okay, and the zero shot is the idea. So maybe let me try to show you once more about the zero shot. So I hope that slowly all of these things will start making sense as soon as we code a little bit more. So let me talk about just a second about zero shot again. So here we have all sorts of letters and numbers, right? That is training set. And in inference set, we have different kind of letters and numbers that were never seen inside the training set. And if we want to use that model without retraining and consider the enrollment samples and then the like second inference after that as a separate training process, that would be zero-shot learning, because you would not actually learn, like train any weights. You would use the pre-trained weights, use some procedures, and just immediately get accurate results. That's why it's a zero-shot learning. So you can think about, like here we have in the training classes, like let's say there are 28 classes for training, and 1, 2, 3, 4, 5, for example, some 5 other classes for the inference. You already see that the way how we formulate the problem, it's a lot different from the classical classification, because in classical classification you always have the same number of classes for each of the phases of the training, testing, validation. Now we have ability to use like different kinds of classes for the actual training, and you don't need to for inference, and we don't need to even transfer learn. We just can use it just as it is. So that was a small information regarding that. Hopefully that clears a little bit at least, because of course I'm not expecting that you immediately get it, but step by step. So here we have the z vector. So the z vector is now unbounded. It can go from infinity. So we have, let's say, 32 dimensions there. If there would be 4 dimensions, then there could be, let's say, something like 0, 1, minus 2.1, 2, minus 5, right? So this would be if the embedding size would be 4 for each of the samples. So so if this would be 4, and then it would be also multiplied by the batch size, of course. So just a small example what I mean by that. So there is just an arbitrary embedding, the latent space, but it's unbounded. So it can be that here would be minus infinity, plus infinity, and so on. This is not like desirable. It's really like your vectors can just float into infinity. That's not fun. So one like very simple, easy way would be to use the spherical space. So we want that each of the vectors of z would be a unit vector length. So we want z to be unit vectors. So you can read up on that. The spherical space very often used in many mathematical problems. So here we can get that by the L2 norm. By the way, the original paper of the Lacoon, I think, mentions that he used the L1 norm. That is like it's not spherical. It's kind of like rectangle. It's kind of really strange why he did that. But it seems like that I read that paper multiple times. It seems like that he used that, but you can double check and let me know if I'm mistaken. So detach. But there is a lot of interesting properties anyway. If it's L1, L2, doesn't matter. You just have some of the properties that are valuable. So here the dimension would be over again the first dimension. So that's why. So the P2 means that it's a L2 norm. So this is a squared one, right? So just the Euclidean distances. And here the dimension 1 means that we don't want to look at the batch, but at the second dimension. And then useful feature would be keep dimensions too. So that's just copy that norm to all of the dimensions of the z. I forgot to mention that I did the detach here, because if I don't do the detach here, it will just learn through that norm, and we'll try to fix that norm so that we can get more so quicker to the spherical space. I'm not sure that that's beneficial. So for this case, I detach it, but theoretically you could also leave it as it is. It should work with the gradient. So, but still. So here we use that one. Then we will divide z by the norm, and we get the unit vectors. So after this operation, what we get now, of course, it will not go to the infinity probably, because the training procedure will prefer it to stay closer to some like closer to that space, the spherical space. But if it would be unbounded, it could go to infinity. So here, the output will be then. What I mean by that is, if we do the torch sum here, torch sum. So you can actually test this later. So over the z vector of some dimension here, it should be 1 basically. So that's a unit vector. So unit vector, very often used in the computer graphics and stuff like that, especially when you calculate normals and all sorts of stuff with regards to, let's say, what is there, like the angles and stuff like that. So if you that they should always be a unit vectors. If you don't make them unit vectors, bad things happen. Okay, so I will copy this part of the code also to the Jamboard, so you can follow up later, and then we'll move to the training part. I will not try to hold you too long today. Probably we'll need another workshop to get it properly done, but at least now you will have some template that you can start working with and thinking about it. And in the following workshops, I think I can go really in depth with all of these stuff. So we have this one. Hopefully it's working. Not sure right now, but hopefully it should work. So then the next part with regards to loss function. So that's, I think, is kind of the most interesting part. Probably that one would be the last thing we do today, and then afterwards I can give as my students as a homework to calculate the accuracy using the center of the mass of each of the clusters. And next time we can do this together as well, just to make sure that everybody gets it. So here there are actually multiple ways how you can then use the deep metrics for calculating the accuracies and the assignment to the classes. One way is using just the closest distance. So that so here we'll have the loss functions. So losses. I just realized that I accidentally deleted the backward parts of the losses, but that you can add as well, not difficult stuff. So here we'll have the losses, and we need to calculate that loss function with the hinge loss or the ReLU or with this max, right? So we can do that. Here is the 4. Again, a lot of ways how to do this. I think one way was using the pdist, so torch.pdist, but I will do this step by step with for loop so that it is more understandable what is happening inside there. Otherwise, if I just use the pdist, then the code is not so readable. So the other thing is that I will do a little bit of sample mining. So sample mining is very common with all of these deep metric learning methods, because usually you cannot consider every single combination of every single sample. So usually you use the sample mining. So sample mining. In this case, it will be hard sample mining. Hard sample mining. So by hard sample mining, I mean the selecting those samples that are the worst samples possible. Like if I want my two vectors to be close as possible and they are farther away as possible, like really like a long distance away, I say that this is a bad sample. So if I have, let's say, class A, sample 1, and then I have class A sample, another class A sample, and if I just like illustrate here some distance, right? So now they are close, right? And now they are like really far away. So and they are from the same class, right? So this is bad sample. So this is let's say how we could write it. Bad sample. So basically this is not bad but hard sample, and this is easy sample because it's really already close. So that's from the same class, and the same thing is also true for if we illustrate with a different class. So we have class B here, so this is a hard sample now, and with the class B here, this is easy sample because it is long distance away. So, and with regards to distance as well, so with this easy sample, there will be the margin as well, right? So if it's over the margin, everything that's over the margin will be easy sample, and everything that is like under the margin, there would be a little bit harder sample. So there's a lot, there are so many things with the sampling strategy, so this is going to be just a dumb, simple strategy. So here, let's write then dists. So these will be the pairwise distances, torch and n functional, I think it was functional, then the pairwise distance. You can have also here cosine distance, that would be, or cosine similarity, and then 1 minus cosine similarity would be distance. That is also a good metric. With the cosine, it's actually really nice properties there. So here, if you use this one, and use then the z vector that we just produced, of course I deleted the z vector as well, sorry. So the z vector we can get from the model, of course, right? So the model forward the x. So we now get the vectors of the z's. So here, if I select the I here, and of course I need to expand it to the same dimension as all other z's that I will compare it. So I go one by one sample and calculate the distances to all other samples in the batch. So we are always looking just in the batch. There are also some proxy procedures where you can look outside the batch as well, but that will just make it more difficult now. We'll look at very dumb, simple procedure just so that it will not take so long for today. So now here there is we're looking at so we're copying, basically not copying the pointers to have the same dimensionality as the z vectors here, and calculating the distances between all of those vectors. So that's first part. Then the second part is then we need to find the hard samples and the easy samples for each of the groups, for positive group and for negative group. So let's start with the negative group. So this negative. So why are you using expand? Because the dimensionality do not match. If I use so let's think about it. So Z1 shape would be actually the embedding size, like that, but the Z shape would be all of the samples in the batch times embedding size, and they would not match, and I cannot do the pairwise distances. It's like it will just calculate the Euclideans over each of the pairs if this one is not the same dimension as this one, and it will go over the first dimension, hopefully. Actually, let me check. I think it by default does it. There is no even the parameter for that, so it will just do the first dimension for the pairwise distances. Okay, and expand is just the same stuff as repeat, or I think the tile. I think not the repeat, but tile. There was a function called tile, I think, or repeat. Sorry for that. So, anyways, so here this clone. I want to clone them primarily because I don't want to calculate them twice, but I know that from documentation, if I remember correctly, when I clone it, it still adds gradients together. So I hope that this works. So I just don't want to calculate the distances twice. Maybe there's a smarter way to do this. If you know a smarter way, let me know. So here, let's set that all of the distances where we have the y class the same as yi class, they would be really far away. So they would not be, so they would be easy ones, and we would not want to look at them at all. So we will call them infinities, like that. Actually, when I see in some of the PyTorch code, I think they use sometimes these infinities to nullify logarithms as well. If you have the, I think how it was done, like minus infinity or something like that. I think for the attention mechanism they do this. So here, these will be non-matching classes, and then if I calculate the j position, so that position that is the hardest one, that is like the closest one. So the closest one we can calculate by argmin, of course. Argmin of the distances. Distance is one-dimensional. We don't need to show what dimension. So these will be the closest distances of the negative pairs. So this is, sorry, of the negative ones. So that's why we want to use these ones. Also, I want to just double check if accidentally I do not include, so it could possibly be that all of the samples from batch are from the same class. Hopefully that would never happen, but like theoretically something like that bad could happen. That's why I should check it. So float is infinitive like that. So if it is not really the case when all of the samples are from the same class, then I can use it, losses append. And here I can use all sorts of stuff. I think like the for the hinge loss. For the hinge I could use the relu as well. Like all of you, I think many of you said that this is the same as relu, and this is the case. So we can use the margin minus margin, and then the dists. Actually, the interesting thing is just to make sure that the clone stuff doesn't mess up stuff. I will use the dists directly from here. So with a J. Like that. So I just don't want to risk that actually the clone would break my gradient. So I think that's fine. Right. So first part is ready. The next part is positives. So dists positives. Again, dists. Actually, we could just better clone it. I don't like it. So let's clone it like that. And then this one will be this positives, the opposite stuff of what we had before, and also the minus infinity, right? So this is going to be the last thing for today. Don't worry. I will provide some materials for the next time so that will be even more engaging. Hopefully, arg max of this one of the disk positives, like that. So this is like very dumb sample mining. And then if this one is over, the positives is higher than minus infinity, that means that there is at least some samples that are from the same class. Okay, that's fine. So then I just want to have the distance as small as possible. This J, like that. Great, so this part is ready. And then the loss part. So the final loss part is just loss over torch mean over torch stack. Let's stack all of these together. Like that, right. And yeah, the few lines at the end you can copy from previous template. I accidentally deleted too much. So basically you could have these lines of storing the loss function and then doing the backward. So that should be added there. And let me quickly check if there is no bugs, and then I will add those codes to the Jamboard. And you can then try, I know my students should definitely do the calculation of after this loop. So there is a very important thing that during the training loop, the embeddings change. So after the training loop, you should calculate the center of the mass or of each of the classes, and then calculate which are the closest classes to each of the center of the masses. So now it seems like it's working, it's just the accuracy is not calculated right now. And using the closest sample to the center of the mass, you can determine which class it belongs to. So we'll do that maybe together next time as well. So far the code is working fine. So I will copy this to the Jamboard as well. So I think that this is it for today. So if you have some comments regarding this or some questions regarding this, be happy to answer if you write me. And I think we have WhatsApp group, we have LinkedIn, we have the Google Classroom for some of guys. So just let me know. So I have done quite a few research on this, and also there are some different approaches. Maybe you have some ideas for the next sessions that we could do even more with deep metric learning. I think I at least have my own, let's say, I don't know, how many sessions that I can do with deep metric learning. So yeah, just to show that on the Jamboard this stuff exists. And so yeah, that's it for today. Thank you for joining. Hope it was fun. you can complete the code yourself and do the accuracy yourself, or wait the next time, do this together, and we will make it even more challenging in next few sessions. Okay, so that's it for today. Hope it was fun. Let me know it was fun.
Thank you very much.
Okay, bye bye.